Welcome to the first case study of the Mobility and Migration module. Here, we'll learn how the shape and strength of one's leg bones, especially the thigh bone, the femur, seen here, and your shin bone, the tibia, seen here, can reveal a fair bit about the type and extent of mobility that someone engaged in over the course of their life. You'll recall that even once we're done growing, our bones are still always turning over through the cellular processes of remodeling. One of the main functions of this remodeling is to deposit bone in areas that are subjected to a lot of biomechanical loading and thus would benefit from being strengthened. The inverse is also true. If the loading on an area of bone decreases, it becomes less dense and weaker due to the lack of stimulus causing remodeling. A model of this is depicted here. The optimum customary strain level indicated in the figure varies per bone and anatomical area as well as per individual, and it can be affected by many variables in addition to mechanical loading, including diet, disease, genetic background, body shape, and age, which all have to be taken into consideration when interpreting the structural properties of bone. The idea that a bone's form or morphology reflects its mechanical loading history during life is often loosely referred to as Wolff's law, after a 19th century German anatomist and surgeon who found that healthy bone will adapt its shape to the loads under which it is placed. Especially the underlying trabecular or spongy bone came to be acknowledged to follow the lines of optimal mechanical support. Our understanding of this phenomenon has, of course, improved considerably since this time, and today the term bone functional adaptation, as developed by Dr. Christopher Ruff, is now used to refer to this adaptive capacity of bone to change its shape or volume in response to mechanical loading. The research field of biomechanics is the application of mechanical principles to biological systems. In the case of human long bones, the diaphyses are modeled as hollow engineering beams or cylinders. In the engineering beam model, we can understand what is meant by strength as the beams or the bone's ability to withstand fracture, and then the resistance of a beam to deformation prior to fracture is referred to as rigidity. Different kinds of loadings exist that can result in fracturing of a beam. Compression and tension act around the long axis of a beam and respectively compress the beam or pull it apart. Bending is the result of both compression and tension on opposite sides of a cross-section. And finally, torsion is a force where the beam is twisted around the long axis, producing diagonal or shearing stresses. The most common application of biomechanics by osteoarchaeologists has been the cross-sectional analysis of long bone diaphyses. In this type of analysis, a cross-section is made at a specific site on the diaphysis of a long bone, allowing the shape of the bone, its diameter, and shape to be observed. The cross-section can be inferred from the bone's exterior dimensions or from X-ray, or most commonly from computed tomography, that is CT scans. Rigidity in strength in pure compression and tension are proportional to the cross-sectional area of the material inside a beam, which in the case of bone is the cortical bone area. However, bones are rarely subjected to pure tension or compression, the mechanically more important loadings being bending and torsion. Bending and torsional rigidity are estimated using a variety of cross-sectional properties, known as second moments of area or second moments of inertia. To estimate bending and torsion strength rather than rigidity, measurements of the section moduli are used. So the fact that a bone's biomechanical properties reflect, in some ways at least, its loading history during life has become a major research area in osteoarchaeology because it gives us clues about a past individual and a past population's behavior. The earlier mentioned researcher Ruff and his colleagues were among the first to apply this approach to a large sample of skeletons from archaeological sites. One example of the change in the shape of the femur shaft between pre-agriculturalists and agriculturalists is shown in this figure. And many studies have compared the long bone cross-sectional properties of hunter-gatherers to agriculturalist populations, usually finding that hunter-gatherers had stronger leg bones because of their higher mobility. So, let's return to the concept of mobility. For past populations, this commonly includes walking, running, paddling or rowing, or riding or being pulled by domesticated animals. The regular daily mode of an individual and population's mobility is referred to as logistical mobility, and it's the most common type to leave a mark on the skeleton. It can be separated into terrestrial versus aquatic forms, as these will leave quite distinct signatures on the skeleton. This leads us into our case study on bone biomechanics by Dr. J. Stock, who looked at 4 different hunter-gatherer populations that lived in different climates and at different types of logistical mobility. Long bones from the arm and leg were studied, but we will focus here on the outcome of the lower limbs. The purpose was to investigate the effect of both climate and mobility on bone cross-section properties. The 4 populations that were studied, along with the size of the sample that was analyzed, the nature of the population's aquatic and terrestrial logistical mobility, and the amount of relief in the terrain are shown here. The results suggested that the cross-sectional properties of the middle of the femur shaft are the strongest indicators of the mobility of the hunter-gatherer populations. The groups with the highest terrestrial mobility have significantly different shapes. A shape that was less circular, as it was more robust in the anterior to posterior, that is front to back plane. And they also had higher values for torsional strength. There was also a correspondence between terrestrial mobility and the torsional strength of the tibia. The effect of climatic differences was stronger in the upper leg bone, in the robusticity of the femur, which suggests the lower limb bone, the tibia, was more selected and more mechanically optimized, and in fact may be the best bone to use to investigate certain aspects of mobility, such as terrain. The tibia's shape may be the best indicator of mobility that involves a lot of traversing of rugged terrain as opposed to flat terrain. Another interesting finding was the greater correspondence between mobility and lower limb bone cross-sectional properties in males as opposed to females. Stock proposes this may be in part due to sexual differences in logistical mobility, as well as the greater diversity of tasks in which females were engaged. Stock's study and many others demonstrate that there's considerable variation in mobility, both within subsistence groups as well as between them. So while on average agriculturalists may have reduced lower limb robusticity compared to hunter-gatherers, there are examples of hunter-gatherers with relatively low levels of mobility and agriculturalists that had relatively high level of mobility. So each population's mobility pattern should be characterized, and the analysis of lower limb bone cross-sectional properties provides the most direct way of doing so. In this video, you've learned about bone biomechanics, which combines engineering principles with the response of bone to its habitual loading conditions, to infer mobility patterns of past individuals and populations. You've heard about research that explored the variation in mobility among different past hunter-gatherers, with findings also showing the effect of climate and terrain on bone's shape and strength. In the next video, we delve into a case study that employs strontium isotopes to reconstruct the migration history of prehistoric individuals and populations. We'll see you soon.